In 1865, physicist Rudolf Clausius formulated two profound principles. The energy of the universe is constant. The entropy of the universe tends toward a maximum. This became the first and second law of thermodynamics. But here is the problem. If entropy always wins, why does the universe keep building structure? What if our picture is incomplete? For more than a century, physicists have tried to modify Einstein's theory of gravity to explain the deepest puzzles of the cosmos. To make the equations work, we introduced two mysterious ingredients: dark matter and dark energy. Together they make up about 95% of the universe. And after decades of searching, we still don't know what either of them actually is. What if these mysteries are different pieces of the same puzzle? And what if one simple idea could reveal the origin of dark matter, dark energy, and predict a different future of our universe? Today, I want to share that idea with you. The second law of thermodynamics tells us that entropy must increase. It explains why hot coffee cools down, why stars eventually burn out, and why time seems to move in only one direction. According to this law, the universe is gradually drifting toward a final state of maximum disorder, often called heat death. But now look around. Galaxies form from diffuse gas, stars ignite, planets assemble, life emerges, organizes, and evolves. The universe is not dissolving into a featureless heat, it's building structure. So why does order keep rising in a world supposedly doomed to disorder? The standard answer is that the universe began in an extremely low entropy state, the so-called past hypothesis. And energy just transforms from a usable form into unusable heat. But this only brings problem to the beginning. It does not tell us why structure continues to grow. The picture changes once we look at how modern physics actually defines entropy. In the 19th century, Ludwig Boltzmann explained entropy as the number of macroscopic states a system can occupy. He expressed it with a simple equation where K is a Boltzmann constant and W is the number of possible microscopic configuration of particles. In low entropy systems, the particles are correlated and the structure itself contains information. In high entropy systems, those correlations disappear. Each particle becomes increasingly independent, and the probability spreads across many possible microscopic configurations. Later, Gibbs generalized this into a probability-weighted sum over all possible microstates, where P is the probability of a particular microscopic configuration. Then, John von Neumann extended the same concept into quantum mechanics, where probabilities are encoded in a density matrix. And in 1948, Claude Shannon generalized the same expression to all information systems. 4 formulas, 1 shape. Each one measures the same fundamental idea: how much information is missing from our description of a system. As entropy increases, structural information gradually disappears. It becomes dispersed among a growing number of microscopic possibilities. The structure becomes less coherent, while the uncertainty of the microscopic state increases. In this sense, entropy destroys structural information. Now let's apply this concept to the universe as a whole. If energy is conserved, our universe is an ideal closed thermodynamic system. And energy carries information, so the total information is conserved as well. Moreover, in 1981, Jacob Bekenstein, building on black hole thermodynamics, showed that the amount of information contained within a region of space is finite. And even more surprisingly, it is bounded not by volume, but by the area of its boundary. This idea later became the foundation of the holographic principle. The universe behaves like a system with limited informational capacity, a finite cosmic hard drive. In quantum mechanics, a closed system evolves by a single wave function. The state can also be written as a density matrix. This is what physicists call a pure state. And for a pure state, the von Neumann entropy is exactly zero, and it does not change at all. Now look at what we just discovered. If the whole universe is the closed quantum system and energy is conserved, then, according to our most fundamental equations, the total entropy is not increasing. The universe is not slowly decaying toward disorder. At the deepest level, its total entropy is exactly zero. Wait, if total entropy of the universe is zero, where does the entropy we measure every day come from? The answer is simple. Our universe stores information in two complementary forms: order and chaos. On one side, information becomes compressed into coherent structures of matter. This decreases entropy. On the other, information is dispersed and transformed into random fluctuations. This increases entropy. Both are constantly growing. But they are not independent. Every decrease in entropy on one side is matched by an equal increase on the other. So while we measure entropy growing in every system around us, the universe as a whole stays exactly at zero. The structure that forms matched by the chaos that spreads. Always growing together, always inside a finite cosmic hard drive. What we call the second law of thermodynamics describes only one side of this balance. But if chaotic information is constantly growing, while total informational balance remains fixed, then something must generate coherence, structure, and order. What is it? There is only one interaction of the universe that does the opposite of dissipation: gravity. The second law holds perfectly in the simple systems where gravity is negligible. Gas in a box, steam engines, chemical reactions. In those systems, energy spreads out and becomes less useful over time. But gravity changes the picture. Within our cosmic hard drive, in some regions, gravity packs information into denser and more structured forms. In others, space expands, heat spreads, and chaos increases. Compression on one side, expansion on the other. The same idea appears when we apply the first law of thermodynamics to the universe itself. In a closed system, energy cannot disappear. It only transforms between heat and work. If the total energy of the universe is conserved, the change between them must be zero. And every act of order must be paid for by heat, and every release of heat must be matched by work. On one side, heat, the drive of chaos. Energy spreads, dissipates, and loses its coherent state. On the other, gravity, the drive of order. It concentrates energy and builds coherent structures. The cosmic web, galaxies, stars, planets, and perhaps even biological life itself. And once you see gravity as the counterweight to dissipation, dark matter and dark energy stop looking like missing substances. They reveal themselves as emergent effects of how our universe redistributes its finite informational capacity between order and chaos. In next videos, I'll show you how this balance naturally produces the dynamics we observe, why galaxies rotate the way they do without invisible matter, and why what we call dark energy may simply be heat generated as gravity builds structure across cosmic scales. Physicists like Ted Jacobson, Eric Verlinde, and many others have explored the idea that gravity is thermodynamic in origin. Building on this foundation, I developed a framework called Timeflow Gravity, a theory that makes concrete, testable predictions about dark matter, dark energy, and the evolution of the universe. If you're a physicist, I invite you to read the paper and challenge the idea. The link in the description. Long before thermodynamics, civilizations across the world arrived at the same fundamental concepts: order and chaos, yin and yang, creation and destruction. We treated it as a myth, but maybe it was the first glimpse of the deepest law of our universe. If so, I suggest an update to our classic thermodynamic principles. The energy of the universe is constant. The information of the universe is in balance between order and chaos.